This tiny chip is actually a nano-sized city, packed with billions of electronic components working together.
Inside, layers stack on top of each other, forming a dense, vertical world of computation.
At the deepest level, we find transistors, billions of them, switching on and off as ones and zeros.
Computers work by pushing electrons between transistors, creating logic at incredible speed.
The smaller the transistor, the shorter the distance electrons travel, and the faster the chip becomes.
Shrinking transistors also means we can fit many more of them onto a single chip. For over 50 years, transistors kept getting smaller, generation after generation. This trend became famous as Moore's Law, predicting exponential growth in computing power. Gordon Moore noticed that chip complexity doubled roughly every 2 years.
But around 2015, this progress began to slow dramatically.
Traditional chip-making methods were reaching their physical limits.
Saving Moore's Law required the most complex machine ever built.
This machine costs hundreds of millions of dollars and pushes physics to its edge.
Imagine shrinking yourself down to the size of an ant.
Now imagine holding a laser strong enough to melt metal.
Your target is a molten tin droplet flying at extreme speed. You must hit it, not once, not twice, but 3 times. All within just 20 microseconds. Each hit turns tin into blazing plasma.
Temperatures exceed 200,000 Kelvin, hotter than the sun.
And this happens 50,000 times every second.
Remarkably, the lasers almost never miss.
The machine also uses mirrors, smoother than anything else ever made.
Scaled to Earth size, the largest bump would be thinner than a playing card.
It can align chip layers with precision down to just a few atoms.
All while parts spin under extreme acceleration.
For 30 years, experts believed this machine was impossible.
Yet today, it exists.
Only one company on Earth can build it.
So how is the world's most important machine made?
Everything begins with silicon, refined from ordinary sand.
The silicon is melted in a special high-temperature furnace.
A tiny seed crystal is introduced.
Atoms attach, forming a massive single crystal.
The crystal is slowly pulled and rotated for perfection.
The result is an ultra-pure silicon ingot. Diamond wire saws slice it into thin wafers. Each wafer is polished until mirror smooth. a light-sensitive coating is applied.
Light shines through a patterned mask.
Exposed regions weaken and wash away. Plasma etching carves microscopic structures. The metal fills the tiny trenches.
The remaining resist is removed.
This cycle repeats for dozens of layers.
The bottom layers form transistors. Upper layers carry signals and power. Each wafer contains hundreds of chips.
Chips are cut, packaged, and shipped.
But the hardest step is lithography.
Printing tiny features with light causes diffraction. Light spreads and interferes at small scales.
Waves cancel or reinforce each other. Engineers design masks to exploit diffraction.
Lenses must capture enough diffracted light.
Higher numerical aperture means finer details. Shorter wavelengths create smaller patterns. Green light prints finer details than red. Physics sets a fundamental resolution limit. Eventually, traditional ultraviolet reached its limit.
What if we used even shorter wavelengths?
X-rays were powerful but impractical.
Extreme light requires a vacuum. Normal lenses absorb this radiation.
Mirrors offered a possible solution.
Special multi-layer mirrors were developed.
Each layer is only atoms thick. Reflections combine constructively. Together, they reflect extreme ultraviolet light. This proved EUV lithography was possible. Many scientists initially doubted the idea.
But a few refused to give up.
Fusion research unexpectedly helped. Tools from nuclear labs found new uses.
Early proposals were mocked.
Then, industry leaders took notice.
governments and companies joined forces.
The first EUV prototype was born.
Eight mirrors guided light to the wafer.
It printed features never seen before.
But it was far too slow.
Factories needed speed.
Each mirror reduced light power.
Only a few photons reached the wafer. A stronger light source was essential.
Early sources could not scale.
Tin proved far more efficient.
Molten tin was sprayed into droplets.
Lasers turned droplets into EUV light.
Droplets had to be perfectly timed.
$50,000 droplets per second.
Spacing errors could destroy everything.
Tin debris threatened precious mirrors.
Ingenious defenses protected the optics. Mirrors had to remain atomically clean.
The system became unbelievably complex.
One company pushed forward alone.
ASML mastered the impossible. EUV machines now power the world.
Every advanced chip depends on them. Moore's law was saved.
Transistors kept shrinking.
Model AI owes its power to EUV.
So do data centers and smart machines.
These machines run continuously for years.
Each one costs hundreds of millions.
Thousands of suppliers make one system. Precision optics meet extreme lasers. Atomic level control is mandatory.
Physics is always watching.
Researchers already look beyond EUV.
Can we go even smaller?
Each step becomes harder. Economics matters too. No country can do this alone.
A single tin droplet changed everything.
Precision defines success.
Clean mirrors mean working chips.
We now build at near atomic scale.
All hidden from everyday view.
Yet these machines shape modern life. They enable global communication.
They drive science and medicine.
They reach into space.
EUV is engineering at its limits.
Many said it couldn't be done.
Persistence proved them wrong.
This machine is the heart of computing.
A nanocity that never sleeps.
The strangest machine ever built.
Built by patience, not shortcuts.
Decades of trial and error.
Failures paved the path.
Physics guided the way. Light writes the future.
Silicon tells our story. The world now depends on it.
And this is only the beginning.
What comes next? It all starts here.
Tiny machines, massive impact.
Engineering meets imagination.
Physics, chemistry, and precision.
From tin droplets to stars.
Yes, it's a little crazy.
But it works!
The most important machine on Earth.
Hidden, yet essential.
Always running.
Welcome to the strange world of chip making.